morning. Because we wrote the paper in the dictionary, we both, Joseph and Frank, like me, and we will expose both. The first part is mine, and the second part is Joseph. I would like to insist on 3 points concerning Penrose. First is the remarkable continuity of inspiration. Second point is the powerful of mathematical point of view, of mathematical point of view is very, very deep and difficult. And the third point is he has a very original point of view in the problem of quantum mechanics. I hope we will introduce to this point with Joseph. No, the fact that we require the world ultimately governed by quantum mechanics, meaning that quantum mechanics is a fundamental theory from which everything can be constructed, implies that we are no longer at liberty to consider the observer as something outside the box. Ultimately, the observer must be defined by the same theory that he seeks to observe. This leads to the measurement problem, which asks if a theory can consistently describe measurement of itself. Solving the measurement problem requires making some assumptions about reality. As the assumptions are arbitrary, they can describe different reality and consequently many interpretations of quantum mechanics. In his theory of relativity, Einstein laid to the conceptual groundwork necessary for deriving the equation of the theory of relativity on the constancy of the velocity of light and the principle of relativity. The latter asserts that the laws of physics should be identical in all inertial systems. We contend that it is the existence of this fundamental principle that explains why we don't encounter numerous interpretations of the theory of relativity. Among the 2 principal motivational ideas behind the original introduction of twistor theory was Penrose's idea that one should seek a description of the physical world that would be fundamentally non-local. The first is a very important non-locality. I had it upon twistor's initial notion in late 1963. I considered that there were some reasonable persuasive indications from the early work of EPR and David Bohm that some kind of spatial non-locality must be true of the real world. I think we were certainly not forced into this viewpoint until Bell's famous result appeared in 1964. One of the most striking elementary of this physical connection appear in the geometry of the spin states of an ordinary speed, 1/2 h bar, particle, such as an electron or proton. Each pure state corresponds to a direction in space, about which we might regard the particle as spinning in a right-handed sense. But these states refer also to the rays through the origin of a 2-complex dimensional Hilbert space. Thus, we have an unambiguous correspondence between the complex direction of the Hilbert 2 space and the real direction of ordinary 3 space. The set of complex Hilbert space direction as a natural structure as a complex projective, the Keller manifold, 1 manifold CP1, while the real Euclidean direction constitutes the ordinary 2-sphere S2. Now, I want to insist on this point. It is very, very important. It is the inspiration by Penrose of the point of view of complex knot. He he say very always that the secret of nature lies in the complex numbers. The essential identity between these two spaces provides a link between, on one hand, the fact that it is complex linear superposition that occurs in quantum mechanics, and on the other side, that ordinary space is three-dimensional. Now, in the twistor theory, we have these 5 points. No-local theory on space-time. This question of no-locality is very important. It is maybe one of the main points in thinking of by Penrose. Large rays more fundamental than events. It is also very important point. Non-perturbative physics constrained by self-duality, and the impact on pure mathematics, very important, differential geometry, integrability, etc., in the twistor theory, which is a very powerful discipline in mathematics. Penrose was always captivated by the mysterious connection between the continuous range of possibility for the orientation of a spin axis within a classical space-time model and the discrete or granular character of the quantum concept of spin axis orientation. Spin network theory was based on one of the most remarkable components of conventional quantum mechanics, where a fundamental concept that is continuous in classical mechanics is discrete in quantum mechanics, namely angular momentum or spin. And many of the most fundamental and paradoxical features of quantum mechanics, such as discreteness and non-locality, are most prominently expressed through quantum spin. For the space-time representation of the wave function of free massless particle or general speed, the Schrödinger equation translates to a certain equation known as the massless free field equation, nabla big A prime phi ABC is equal to 0, is symmetric in its n spinor indices. The equation being the conformally invariant free field equation for a massless field or spin n over 2. So it turns out remarkably that there is an explicit contour integral expression that automatically gives the general positive frequency solution of the Hilbert-Massless free field equation, simply starting from the twistor function f of bit z r. In fact, the expression also works perfectly well with this positive frequency requirement. So the requirement is easily answered in twistor formats. The mass field equation seems to evaporate away in the twistor formats, being converted in effect, that is very important as well, the pure holomorphic CT, and Penrose speak about the holomorphic ideology. When we examine the expression more carefully, we find that there is an important subtlety about how a twistor function is to be interpreted. And this related a stringing way to the positive-negative frequency splitting of massless fields. This subtlety is also crucial to how twistor function manifest themselves in active and provide us with curved twistor space. What is this subtlety? It is that twistor functions are not really to be viewed as functions in the ordinary sense, but as what is called elements of holomorphic sheaf cohomology. That is maybe a little complicated from mathematical point of view, but holomorphic sheaf cohomology concentrates many aspects, characteristics of this discipline by Penrose. These ideas of the sheaf cohomology are fairly sophisticated mathematically, but actually very natural. Now, think of a manifold, but you can reach the transition function f or ij differ from the entity by only an infinitesimal amount. In fact, the class of function f ij that one might be concerned with in cohomology theory can be extremely general. In twistor theory, one normally deals with holomorphic function. This gives us the notion of holomorphic sheaf cohomology. And it is my last slide. An important feature of cohomology is that it is essentially non-local. This non-locality for twistor function tells us that there is no significance to be attached to the value attained by fij at some particular point. We can indeed restrict down to a small enough open region voisinage surrounding that point and find that the cohomology element disappears completely. No, Joseph.
Okay, I will tell you a story more than read it, I think. I'll show you exactly what I'm talking about. Because it's a question of, okay. So I would not to read all things, I will tell you the story about this. Because question of locality already, you see the Penrose by concern, but there is more than this. The idea behind, because entanglement, what is the entanglement for question continue? Because we have things for measurement, and you see the two particles. The fact that you have to understand what exactly happened. When you have your children, they are very small, and when they say something, you make expression in their faces, and they try to understand what you are saying. You see, and sometimes they laugh, even though you don't say nothing funny. Why? Because you don't understand what you are talking about. You see, so they didn't have conceptually all the foundation to understand what you are talking about. You see, we are in the same position. We have foundation. We have poor concept, new quantum mechanics. You will see why I will show you why I say this. I will say with my little story a little bit. You see, that object is not possible to realize in our space. That's we call it impossible figure. Why? Because it's very complicated object from quantum group of space. You cannot do it. Now, if I cut it somewhere, I only cut it. We have 3 pieces. It's easy. So we can do it 3 pieces in this space-time, but globally not. You see, so the globality is not the same as locality. And cohomology, that exactly cohomology, it's they told you what the abstraction to pass to something is feasible locally, but not globally. That's exactly the sense of cohomology. For this, well, the entanglement is a global concept. You see, when you make measure, it became global. And you cut the entanglement. And this is sense of cohomology. Why our space-time is not exactly what you think about it. I will show you more this kind of story. Here exactly inspiration from that T-bar of Penrose figure, you see. Here people walking here in this kind of figure. And see, they are walking. They are no level. They are no level. So no propagation. You see. But if enough one person cut it, and then you start having a level. You see, you have quantization. You see, that's a problem. So what happened? Why? We'll take example, illustration. Fourier equation, heat equation, and Schrödinger wave equation. You can pass from one to the other by introducing d by it, by complex structure. When you add the complex structure, Fourier equation became Schrödinger equation. Fourier equation is about statistics, about probability and motion of particle, material things. Schrödinger is about localization in space-time. You see, Schrödinger talking about localization space-time, and Fourier talking about matter. But if you change T on IT, you make connection. So you understand why Schrödinger equation has statistical interpretation. Because when you take your Fourier equation and make an interpretation locally near the point, you will find Schrödinger equation. And that's in sense why quantum mechanics is statistical. Because you get the now, what is the source of complex structure? Why do we have complex structure? The answer is very complicated. I'll give you only the why and how could it exist. Because it's no commutative geometry. Our space-time intrinsically is no commutative geometry. And complex structure only signature of the no commutative structure of our space-time. That's exactly what complex number. Complex number only is relation of some structure of space-time which is no commutative. And that's exactly how I understand it. And said that Heisenberg and equation uncertainty is exactly no commutative geometry. And he came with the idea that we can introduce some geometry for quantum mechanics. It's no commutative geometry. It's not the Euclidean geometry, you see. Now, if you check more on this, I would like again for this figure here. This figure is not associative. You understand what I'm talking about? So it means that the complex structure, you have commutativity as a number, but still you have associativity. You have no commutative geometry, but still have associativity. So quantum mechanics is still associative, but not commutative. But here you can have an entanglement. Entanglement is not associative. So we don't have mathematics for no associative. If you take a quaternion, it's only 4, and you still have associative. Now you take octillion structure, which means 7 complex number. You will have something very bizarre, no associative algebra. We don't know exactly how to mess with this kind of thing. We start having it. What I'm interested that if you take this kind of thinking about space-time as not associative globally, not locally. Locally you have associativity. Globally it's not associative, but locally still. You see, when you take a point somewhere in this, I think you can find the same thing locally, no problem. Globally is not associative. One interesting thing, if you develop your theory in that associative space, you will have curvature. Not associative to give you that curvature. So what you call curvature in geometry is a result of not associative globally. You see? And that's what I'm talking about, that the problem with quantum mechanics is not a quantum mechanics problem, only we didn't have the language, enough conceptual foundation to understand what we're talking about. And that's given to us. So back again to the children, we are children. And we are trying to understand the nature, and we have to develop our language. That's it. Thank you very much.
We have time for a few questions, and we'll have coffee after that. Neither associative nor non-conditional questions.
And we don't fit to that question because we are already organized, so we have to sacrifice for time. No problem.
Well, certainly time for more discussions, including over coffee and treats. But if there are no immediate questions, why don't we then pause and we'll have our refreshments?
Yeah.
Okay.
Okay.
Well, let's thank the speakers again.
Thank you very much.